Was that it? That was it. And so I asked you to write that as a linear system. Yeah, and why did I do this to you? We've done these sort of fluid models before. We've had all sorts of approximations like this, and all ones you just take conditional means of both sides. So the conditional expectation of xt plus 1 given xt is just the mean of this. That's xt. And so it's sort of like a fluid model type question. I just want you to know that was my intention. But half of you just panicked on this question. I'm not sure what happened. But I wanted you to write this where this was sort of like white noise, zero mean white noise. So if you take conditional expectations of both sides, you can see I'm just asking for you to write alpha equals theta. So there's the answer. So I don't know. So this, for some reason, half the class just had a total panic attack on this question. So this is a noise. Luckily, it was done independently, so those of you who got lost here, don't panic. The next question was just a common filtering question. All right, so anyway, so that's a common trick. So this is the mean of this, so this is independent of this, so it's a zero mean stochastic process. The mean of this is theta. And that's independent of that. So the expectation of this is the product of the expectation. So. All right. This sort of trick also, the other reason I put this in is I wanted to torture you a little bit. Because it's a trick that's used over and over again in stochastic approximation. So, stochastic approximation, we have this recursion like this, where the goal is to find the roots of the mean. Okay, so this is a d-dimensional recursion. So we're trying to find theta star and RD that satisfies this equation. And we see I've given you lots of motivation. So Q learning, TD learning, SARSA, and all sorts of other algorithms or instances of stochastic approximation. They come everywhere. And so when these algorithms were developed, when TD learning, Q learning all were developed, the people who developed them didn't know about this theory. And they just hacked away, and half of the things that didn't work, they didn't publish, and they had one success, published a paper, and no theory to back it up. And it took a decade almost for Ben Van Roy at Stanford, at MIT, to say, hey, this stochastic approximation is a theory for this, So once you know this theory, you can crank out algorithms all day long. It's really cool. There's a roadmap for doing it. And so I'm not going to go through a stability proof because I want you all to be mathematicians. I'm doing it because it's the only way you know how to design a useful algorithm. When it doesn't work, it's because you've got a sign error here. It should be a minus sign instead of a plus sign. Or you have a lousy matrix gain here. A could be a matrix. We'll keep it scalar for now. or something else. So you need to understand convergence. Convergence and also variance. That should be inverse. It turns out that the right scaling, if you want to know the variance for large T, it's going to be, that's right, it's going to be, we'll multiply by 1 over A of T. Okay? So if A of T is typically 1 over T. For a scalar gain algorithm, that's what you typically use. And so A of T inverse is just T. And so it says that this variance goes to 0, like 1 over T. And sigma then gives you the gradient, the constant, the scaling of how fast it goes to 0. This is a matrix, right? A vector times its transpose. This, for TD learning, might be the number of atoms in the universe, and for Q learning, only 1 million. It can be infinite, too, depending on the gains. It can be infinite. So even though you get convergence, depending on this model, it can be infinite. And the linearization is all that matters. It turns out that the linearization of this equation is how you get the variance. So I'd love to do this. I mean, I think that that's the remainder of the course, is to explain to you the mechanics of stochastic approximation. And it could be a whole course if you wanted to. But I want to give you today, I want to give you the main ideas of convergence. And it's like everything, it's mainly notation. A couple of really clever steps, but mainly it's notation. And I really thought about just bringing a projector, but I do have lecture notes. I'm not bringing a projector, I'm bringing slide. But this lecture notes I'll send you a link to. But I would say that for this, my paper, seriously, my paper with Borchart's book, is the best source. I gave you the reference already. And so it's pretty similar to my lecture notes. Let's see, there you have it. He does a horrible job on this. I could kill him. He'll be visiting in February. He just, I don't know. He forgets that somebody might actually read this book. But he does a good job on this.
So for that question on the exam, even if it wouldn't make sense, theta could be anything from 0 to 1, right?
Oh, no, to get 0 mean, there's going to have to...
Oh, you have to have...
It has to be the mean of G.
To get 0...
To get 0 mean, yeah.
Okay.
You get 0 mean. Yeah, there's only one, as far as I know, there's only one answer to that question. This is what I wrote down. I didn't expect that. I was not trying to create a mass panic. So let's check this out. All right, let me go through the steps. So I have, lecture notes from 10 years ago that have been on my website in Illinois ever since then. And I meant to send out a link to you all, but I'll do that later. So again, let me write this down again. Well, let's keep that there, where we can go back to it. So there's like there are two standard cases. I'm going to assume in this lecture that n is ideal. Okay? It doesn't actually have to be, but it could be Markovian, it could be all sorts of extensions, but let's assume it's ID. I just told you that typically we take A of t to be 1 over t, but also, that should be plus 1, I guess. But there's also a constant gain algorithm. And then what would you call this recursion based on this course? If A is constant, what kind of process is that? It's a Markov chain with stationary transition probabilities. That's right. So it turns out that under the conditions we'll talk about, the stability conditions we'll talk about. You can address it using generalizations of the Lyapunov conditions I've talked about before. And what you find out is you can get some variance bounds. If A is constant, you don't expect convergence. It's ergodic. But what you can show is things like this, that the expectation of theta tilde of t squared things like that. That's what you can show. Big O of A, I mean, less than a constant times A. Sorry. And I'd love it if we had another few weeks of this course. It would be fun to show how you develop generalizations of this drift condition to get ergodicity and prove bounds like this. But it would take, we'd be going on until January, so we won't do that. So we're going to look at this vanishing gain case. And these two conditions are critical. That you have, that the summation of A has to be infinity, so you have, so you can travel long distances. So you're not limited in how far you can walk. And this has to be finite because you end up injecting noise into the system, and you don't want there to be too much noise. And that'll be explained as well. But there's also this Polyak averaging. Forget the second thing. Let it be huge, something like AI equals, what would be like 1 over, there's one for you, something like that. And you know what he does? He runs stochastic approximation, and then he averages it. Isn't that crazy? Why on earth would you do that? You crank up the gain so that by something like this, it's like high gain, it's like super high gain. You end up, the noise here gets, you're introducing way more noise than you like. But then he averages the result, and he finds this convergence. And in theory, this has optimal variance. That's in theory. I mean, I've done experiments and experiments and experiments of this, and in real simulations, I can't see it. So you can prove that this sigma the variance that I defined for you, is minimal using this averaging scheme, but just empirically I can't see it. It's strange. So one more thing you can do. So this is what I'm going to talk about today. Another thing you can do is you can take A of t to be a matrix, and if you choose it correctly, you can also get an optimal. Go back to look at your notes. You'll see I defined this a little while ago. You can also optimize this, and there empirically, man, you can see it. Yeah, and that's what I call stochastic Nunn-Rapsin. And so this would be TD learning. This would be Q learning. That's what's actually happening in this row. So the reason that Q learning works so much better than TD learning is that here you're actually, it's really a matrix gain algorithm. That's what it turns out to be. And that really is, I mean, didn't look like it, but that's how it can be. So for the remaining lectures of the course, I want you to understand why you get convergence under natural conditions here. I'd like you to at least see this. I'll actually be able to, it's very simple to see why this is the best thing to do. I won't get into this. It's too technical, but I can give you references if you like. All right? So there are the issues I'd love to, at least for you to know before you celebrate Christmas. All right. So we fix this theorem. So, what are the steps? So this is actually, unfortunately, I have to leave this out of the course too. Somehow, you prove that this recursion is stable. And there's some beautiful ways of, this is the easy part in a way. And if there's time, I'll give you some conditions. But what I mean by that is there's a bounded set. Some bounded set in RD, and theta of t is an H, that's what I call H, for all t sufficiently large. So in order to get convergence, you first have to verify stability, that the recursion doesn't blow up. And I guess I will have to explain this in another lecture. But it turns out that basically, under the very, very mild conditions apply, okay, which we'll talk about today. So right now, we'll just assume it. In fact, just to make the analysis easier, I'm just going to assume it's true for all t. Now, that's unrealistic, but what I'm really doing is I'm changing 0. So this says for all sufficiently large time, I'm in a set. Well, but that time might be 1 billion. All right. I'm going to call 1 billion 0. That's all I'm saying. Okay, so just for the sake of simplifying the discussion, I'm just going to assume theta t is always in this bounded set. Another thing you can do is project. Whenever you leave it, just pop it back in. That's step one. We need stochastic stability. So this is something a lot of you haven't seen before. I'll explain to you what I mean by this. Stability of this ODE in the sense of Lyapunov. The ODE it's the usual fluid model ODE that we've talked about before. So it implies in particular, and I mean asymptotic stability. That's the standard language. Asymptotic stability in the sense of Lyapunov means in particular we converge. I forgot one more adjective. It's global. For any initial condition, I converge to theta star. Right? So this is how you construct the algorithm. You know, basically, I'm trying to find this theta star. I know it's from some fixed point equation, or you know, from some nonlinear equation, and I'm going to have to design f bar to get this. So that's why I might have to put a minus sign in front or something. I might have to put a gain in front. I might have to fool around with this in order for this to be true. So this is a design step. A lot of choices in f bar. You know? Again, if f bar of theta star is equal to 0, then m times f bar of theta star equals 0 for any b by d matrix m. Yeah? Right? So I can take that and call that f bar, and I can choose m to get stability. Or maybe, hopefully, I can choose m to get stability. And m could depend on theta. Still true, right? You know, but m depends on theta. This is a design question, how you design a matrix M.
When we say theta t belongs to H in this definition of stochastic stability, do we mean theta belongs to H with probability 1?
Yeah, that's right. So yeah, for every realization, there's a time that depends on. Yeah, that's right. It's probability 1. Okay. All right. So 3. So this is sort of setting things up. So here's a key step. Is that true? No, that's not true. What do I mean? Well, that was the point. I stuck this in the exam just to shake you guys up. So there's a mistake here. So what do I mean by that? Well, basically just take differences. I'm going to define that delta I had before. First, I'm going to say that in this recursion, I can add and subtract f bar. So I can say that my noisy f is my deterministic f plus an error term. And so that's the reason I stuck this. I haven't defined m yet, I know. But first I'm just saying that I can take my noisy thing and write it as a deterministic object plus noise. You know, this is basically something minus its conditional mean. You think of this as noise. And then M is just the sum of these deltas. So M is accumulated noise, if you like. And the fact is it's being multiplied by this constant, which is going to 0. You know? And one thing to notice is this. Those deltas are uncorrelated. This is something minus its conditional mean. It ends up being that these are uncorrelated. So if I look at the expectation of m of t squared, it's going to be equal to the summation of these guys squared because they're uncorrelated. And notice you get ai squared. So this is where the fact that ai is square summable is crucial. That there's noise being introduced in the system, but its total variance of the entire time horizon from 0 to infinity is going to be bounded. You know, so it's a vanishing noise; it disappears. You know, so there's something here that becomes negligible for large time. And doesn't that look familiar? Doesn't it look like almost like an integral representation of an ODE? You know? So here's where everything falls apart. It's just that realization that we've got noise that you know, is bounded under the assumptions we'll make. Because delta is a function of theta, theta is in a bounded set, and all that, so it's going to be bounded. And so now it's just a matter of comparing an ODE with a approximate ODE driven by a little bit of noise that's vanishing. There's the main concept. We could almost walk away. I want to tell you there's like one main mathematical tool enabled to make that intuition precise. Okay, so how do we do the comparison? I want to compare now theta to the solution of an ODE. For that, I'm going to fix a time window. This pen's going too. Okay, so I'm going to fix a time window t, which is really big. And I'm going to do some sampling. So I'm going to think of Tn, sum from 1 to n, is the times at which I sample a continuous process. Now that wasn't how I got here, but so I'm going to compare the ODE with a stochastic model. So I'm defining just that, which are going to become sampling points. And notice that goes to infinity. And our assumptions, Tn goes to infinity. And then, but I've said I fixed it to capital T. What's that for? So what I'm going to do is I'm going to look at blocks of approximate length capital T. So I start off with a time t equals 0, and then I'm going to wait for the first time take n equals 0, the first time that my sampling, my sequence of samples gets larger than 0 plus tn for the first step. Okay. So what I mean by this, tn plus 1 minus tn is greater than t. It's the minimum of tj such that tj is greater than tn plus t. So the difference between that and that is going to be greater than t. But it's the first time, and these tj's are getting closer and closer together. So what I'm going to actually do is I'm going to look at the window of a length approximately t, from tn to tn plus 1, and compare the ODE with this on those windows, and get a uniform bounds, and then let this box footage there. Really, really cool trick for analysis. All right. Okay. Again, this is interpreting. This is just interpret. It's going to end up being a sampling time. Is the interpretation, and I've got these blocks tn to tn plus 1, of approximate length t. And then on these windows, what are we going to do? Representation again. Running out. Let's see. Okay, so I had this representation for theta. This is discrete time. I'm going to go to continuous time. Okay, so the first process is just this, but instead of calling t time, I'm calling t sub n time. And that's because of the fact that, hey, this looks, without the noise, like a approximation of an integral. And these AIs then would be delta t. This is like dt. That's the idea. That tn minus 1, that's a delta t. Delta t right there. So this looks like an integral. Exactly. Where these are, and so I want the sum of dt's to be my time interval. And that's why I'm using tn as my time. Okay. So that's easy. So I'm just taking this representation and making a continuous time process through piecewise linear interpolation. So it's continuous. It's piecewise continuous. Piecewise linear, is actually what to say. Sorry, that was a big typo. I was thinking it's continuous and piecewise linear. That's what I meant to say. And I'm piecewise linear. Okay? Piecewise, linear, and continuous. All right. Okay, so there's one thing that's fixed, psi of t. There's another guy here. I'll put an n on it once, but I don't want to have to keep that n carried around all the time. So there's another process that's a function of time and n, and it's a solution to this ODE on the interval tn to tn plus 1 with the same initialization. Actually, no, I don't need that. What am I saying? I'm going to, excuse me, I'm going to keep on redoing this. I got confused. I don't need that. I don't, it's one function of time. But this is not continuous. So it looks like it should be continuous. It's a solution to an ODE. That's continuous. But it's on this block of length approximately to capital T in length. And I'm going to reinitialize over and over and over again. So I've got this, they start off at the same place. The solution to the ODE might drift away very fast, who knows. The piecewise linear guy is going to like this. But at this time, this would be T1, and because this is T0. At this point, you reinitialize. Well, psi of t is still this piecewise, continuous and piecewise linear process. This psi hat process is going to be reinitialized, so they match up at the initial time. And what we really want is them to match up in the whole time interval. And they will, because the functions erased, they have the same representation, essentially. And I could kill myself erasing that little bit of text. I could kill myself. So everybody take out your notes and stare at that text that I erased. Didn't mean to do that. We'll come back to it. We'll come back to it. I need some other stuff first. So we've got all that there. Yeah, come on, wake up, wake up, wake up. It's only 10 more minutes. We'll be done. There's just a few concepts left, okay? But I hope you're all with me. I mean, that's theta 1, theta 2, theta 3, theta 4, theta 5. And we're just creating a piecewise linear process from it. And that's just a solution to the ODE, reinitialized so that they're exactly the same place in times Tn.
And how do we choose the big T, the time interval?
Oh, right. Thank you very much. Step 6, how do you choose T? That's great. Here's where the epsilons and deltas have to come in, okay? All right, so these are small numbers. So what we're going to show is we want This is what you do to prove convergence. You say for all epsilon greater than 0, for all epsilon greater than 0, the limit supremum of this error is less than I'll put a less than equal to epsilon. And since epsilon's arbitrary, that's the definition of convergence. Okay? And so what we're going to do to choose t is we don't have much of a handle on theta star, but we do know a lot about this guy. Because this is a solution of an ODE that wants to run to theta star. So here are the assumptions. So we've got this ball centered at theta star of radius epsilon. And that's what we'd like to do. We want theta of t to be in that ball. I'll make it back to lesson. Okay. And then so this is the definition of stability in the sense of Lyapunov. That the definition of stability in the sense of Lyapunov, the local stability, is that for any epsilon, they can find a delta. So if you start off in a really close to theta star, you'll stay within that distance epsilon for all time. You know, so necessarily delta is less than epsilon. Okay? So it's true for all time. All time. Right? That's local stability. That's a delta we'll choose. And now, but we have to use this global stability. I want to use the fact that at the end, this thing is at theta star. So now I'm answering your question. Oh, stop clock. So for the ODE now, here's where I'm using asymptotic stability. I've got this bounded set, and I can choose t such that this x of capital T, the time horizon we chose, is in this tiny little ball around theta star for any initial condition in H. So what I've written here says that theta star is like right there. Because I start out in H, and after this time capital T, I'm with this little tiny ball around theta star. So even though I'm resetting this over and over again, I'm then waiting a time horizon of at least t, you know, and I should say t greater than equal to t. Not just that time, because this interval from 0 to t1 and t1 to t2, they're all greater than equal to t. And so if I've waited that long, I'm practically on top of theta star. Where this distance here is delta over 2. You know? And so what's really beautiful here is that I get in this ball, and if I didn't have to reinitialize, I'd be within epsilon forever at theta of t. Cool. So we're done, practically. Except we're not, because there's only 2 more minutes. How do I gracefully exit? You guys have put up with me going over for months. I'm not going to finish, but I'm going to go over a few minutes. So was that 6 or 5? I might have jumped a step.
5 is representations.
Huh. I think I might have skipped a few things here. Anyway, whatever this is, huh. That's funny. I don't know. So. And so let me go back. This is the thing I raised before. Except for now, instead of starting time 0, I'm starting time tn. Because I want to compare the orange and green curves only on these blocks. Okay? And so there's sum over j. What j's would it be? I don't know. J such that I don't know. It's a sum over some j's. The j is such that the tj there is between capital Tn and the tk that's interested in, okay? And so I just want to say again, this looks just like without the noise there, this looks just like a approximation of a regular integral. Okay, and it is, okay? This is how you define an integral. Is you look at delta t's like this, and you let delta t go to 0. It's the definition. Okay, so I can write this as an integral instead of a sum, and I'll just introduce a little more noise. So this epsilon n appears from two sources. It's because of this difference here. Now remember, the variance of this thing is going to go to 0. And then it comes to the fact that I'm approximating a sum by an integral. A sum by an integral. Okay? And there'll be some error, but it'll go to 0 because the AIs are going to 0. So it gets to be a finer and finer approximation. And of course, we also know that psi hat of t is equal to psi tn Now I've introduced an error here. Can anybody tell me where it is? This time it really is a test. It's not a test. So remember, ddt psi hat of t was f bar of psi hat. So does that look like the solution to this differential equation? That's supposed to be an integral form of a differential equation, integrating both sides. They're not the same, right? What's a mistake? I'm trying to wake you guys up. Well, there's a hat there and a hat there. So there's a mistake here. But not there, because we're reinitializing every end. And that's the thing, is that these things look really identical now. There's just a bit of noise here that's going to be. So, you know, if many people now would walk away, and now we have to, because we only have a minute left. So you need a bit of machinery. So how do you analyze differential equations with noise? So given the fact that this noise is going to 0, how can we then infer that this difference goes to 0? It requires some assumptions. So it's almost a perfect time to stop. So I'm going to give you one tool, which is a Bellman-Gronwall lemma. And it's so sad, you'll be all stuffed in turkey. But the Bellman-Gronwall lemma is something that allows you to say that, well, given this, we know that this is practically the same as that. If these guys are the same, it means you're not jumping very much. And if you're not jumping very much, then you're always, then you're always near theta star. Because that difference is delta over 2. And if you're that close to theta star, the OD, if the OD is that close to theta star, it stays that close to theta star forever. Okay, so there's one thing we missed, which is the Bellman-Gronwall lemma. So it's sort of a perfect time to stop. All right. So good man. Anyway, so more to come, and have a good Thanksgiving.